Okay, dear students, this is the continuation of yesterday's lecture. Okay, so we are studying thermodynamics. Yesterday I taught you about we were at the beginning of thermodynamic processes. So what I told you, to study the change of thermodynamic processes from initial state to final state, what we study is, I taught you about macroscopic properties, how we study macroscopic properties for the change of a thermodynamic system. Finally, what we talked about was state variables. Okay, state variables, and I told you that how many state variables are there: pressure, volume, temperature, and mass. We were left with these. Okay, but then I also told you that volume and mass are dependent on each other, right? Because volume is an extensive property, it depends on mass. Therefore, instead of these two, we can take only one, we can take volume, right? Because if we know the value of volume, we can calculate mass. Okay, so we can take pressure, volume, and temperature. Only these three: pressure, volume, and temperature. Which means to specify the change occurring in a thermodynamic system. What does change mean? In going from initial state to a different state, which is called final state, we have to specify only these three variables: pressure, volume, and temperature. Okay. Now, so if we take an ideal gas, what's the ideal gas equation? PV is equal to nRT. In this ideal gas equation, if we take 1 mole, so N will be 1, PV will be equal to RT. We know the value of R, right? R is constant, gas constant. If we know the value of R and we know the value of PV, we can easily calculate T, which means for an ideal gas, if we know two variables, the value of two variables, the third variable can easily be calculated. That means to specify the change of 1 mole of an ideal gas, we don't even need these three variables. We need only two, right? We need either PV or we need PT, whatever. But usually for an ideal gas, we take P and we take T, because pressure and temperature are independent variables and volume is a dependent variable, right? Volume depends on pressure and temperature, fine? So, what did we conclude from this? We concluded that to learn about thermodynamic changes, right? To go from for a thermodynamic system to go from initial state to final state, that is for a thermodynamic process to occur, we need to specify some variables which are called as state variables. And for a monocomponent, single component thermodynamic system, we need three variables to study. Okay, pressure, volume, and temperature. But if we take an ideal gas in 1 mole, then we need only two. But you have to remember these, because usually we don't take 1 mole in ideal gas, right? Usually the gases that we study are real gases. So you have to remember this thing, that for studying the change of a thermodynamic system, we need to specify three state variables, namely pressure, volume, and temperature. Okay. Now, I told you that for thermodynamic process to occur, these three variables are to be studied. Now, on the basis of changing of these variables of a thermodynamic system from initial state to final state, we can divide thermodynamic processes into different types. What are the different changes of these variables that occur, and accordingly what's the type of thermodynamic process? Okay, so what are they? I request you all to keep pen and paper handy when I'm giving my lecture, okay? So that you can write down things of your own. You can even pause the lecture and write down. And you may also write down whatever doubts you have, because you can write to me about your doubts. So, now, where are we? Okay, types of thermodynamic processes. Okay, what thermodynamic processes have you heard about?
I Isothermal, adiabatic, isobaric.
Isothermal, yes. What else?
Isobaric,
Yes.
adiabatic.
Isobaric,
Adiabatic.
yes. Anything else? Isochoric. Isochoric. So these are the different processes, thermodynamic types of thermodynamic processes. Isothermal processes, isobaric processes, adiabatic processes, and isochoric processes. What are they? In these thermodynamic processes, the system goes from initial state to some other state which we call as final state. And what happens in each of these, we will divide them into columns and do a comparative study of these. Okay. So isothermal, right? Adiabatic. What was the other? Isobaric and isochoric process. Okay. So isothermal process is that thermodynamic process in which, while going from initial state to final state, that is, while the thermodynamic change occurs, the thermodynamic process occurs, the temperature of the system remains constant. Temperature of the system, or we can write it like this. Temperature of the system remains constant. Whatever happens, but the temperature remains constant. Okay. Let's go to these first. Isobaric. In isobaric process, bar is the unit of pressure, right? So isobaric process, iso means same. Isobaric process means in that thermodynamic process in which, while going from initial state to final state, the pressure of the system remains constant. Right? And isochoric, in going from initial state to final state, when the system goes from initial state to final state, the volume of the system remains constant. Okay? In an adiabatic process, what happens? In these processes, when all these things happen, there is an energy change between system and surroundings. You give energy to these systems, and that energy is utilized to bring about this change, to change the system from initial to final state, right? So in these three systems, you are giving external source of energy. Then these changes occur. But in adiabatic process, whatever happens within the system. There is no energy change with the surroundings. That means change in energy with the surroundings does not happen. There is no change in energy, no exchange of energy. Energy or heat. Heat is a form of energy. No exchange of heat or energy with the surroundings. Okay? Now see. Now we will see if these changes are not happening. These are constant parameters, right? If these parameters are remaining constant, then what change? Then how does the change happen? What occurs? What happens, right? So here temperature of the system remains constant. Now see, we will take a system. This is our system, okay? There's a piston fixed in it and there's a gas inside it. This is our system, okay? Now its pressure is P1, volume is V1, and because what state variables are we measuring? What are the state variables that we are measuring for us for understanding the change of a system? I told you earlier, the state variables: pressure, volume, and temperature, right? So these are the three variables that we are going to study. So here in this system, the pressure is P1, volume is V1, and temperature is T1. Now you are giving an external source of energy in the form of, let's say, heat, Q, okay? So you are supplying heat to this system. Pressure is P1, volume is V1, temperature is T1. Now we have the final state, right? This is the final, the system changed, okay? the system, a process occurred, a thermodynamic process occurred, and this is the final state where your pressure will be what?
P2,
P2, volume will be
V2,
right, temperature will be
T2.
T1, because temperature of the system
Okay.
remains constant. So temperature will be T1. Okay, T1, V1, T1 will become P2, V2, but temperature will remain constant. Now see, has the volume changed?
No,
Volume.
no, yeah,
Yes, the volume has
Changed.
changed. So this piston will come here. That means the volume has
increase.
changed. Volume has increased because you are giving external source of energy,
Mm.
right? Now when you are giving this external source of energy, okay, I forgot to explain one more thing. Let it be here. Before we take up these 4 processes, I'll tell you something else. Okay, I'll explain something to you. Let's say this is a thermodynamic system, okay, and we are supplying heat to this system. We are supplying heat to this system. When you supply heat to a system, what happens to this system? What will happen to this system? It will change, right? Change will be brought about in the system. What kind of change will be brought about in the system? In a thermodynamic system, if we supply heat to this system, the energy of this system increases. The temperature of this, it will go on heating up and heating up and heating up, right? So its own energy, it's the energy of this system, its own energy, which we call as internal energy, right? We have to study these concepts later, but you need to know a little background of this here. So the internal energy of this system will increase when you supply energy or heat to a system. The internal energy of this system will increase, right? Plus, what else will happen with this heat? The remaining portion of the heat that you supply to a system will be utilized in work done by this system to bring about a change. For example, if there is a change in volume, right, or pressure, it will go here. So this would be the amount of work done, right? Right. So the heat energy that you supply to this system will be utilized, 1, in increasing the internal energy of the system, 2, in performing some work by the system, right? So that means Q would be equal to change in the internal energy of the system,
Plus work.
right, plus work done by the system. This is one of the forms of first law of thermodynamics. Okay, we have to study that in detail later on, don't worry. But you need to know this little bit here. What you need to know is that whenever you supply energy to a system, this energy is utilized by the system to increase its internal energy and to perform some work. Okay. And since this internal energy, how do you know that internal energy has increased? Because when this system goes on heating up and heating up and heating up, its temperature changes or its temperature rises. That means its internal energy has rose, right? That means delta E, we can say, is a function of T, temperature. Delta E is a function of temperature. That means for a thermodynamic system, when temperature changes, internal energy changes. When temperature remains constant, internal energy remains constant. Correct. Now come back to this. I had to tell this earlier, I forgot. Now coming back to isothermal process. In an isothermal process, when you supply heat to this system, to this thermodynamic system, temperature remains constant, right? But the volume has changed. Some work has been done, right? Some work has been done by the system, right? So internal energy is not changing. Why? Because the temperature is remaining
constant.
Since the temperature is constant, that means the system itself hasn't absorbed any energy, right? The system hasn't taken up any energy to itself. The entire energy, however, has been utilized to perform the work. Okay. So what can we say? Q is equal to delta E plus
work done.
W, right? But delta E here is 0 because no change in temperature has taken place. That means entire heat energy Q that you supply to the system has been utilized to perform the work by the system. Therefore, internal energy did not change. Internal energy is constant. So, and what type of work has happened here? The piston has gone up. Volume has increased and pressure has decreased because the gas is relaxed, right? So we can say that this work is pressure volume type work. You must have heard about this pressure volume work, right? So that is why when temperature of a van in going from initial state to final state, upon absorbing external energy, temperature remains constant, pressure and volume have to change, right? Pressure and volume have to change because temperature is remaining constant, internal energy cannot change. So the entire heat has to be spent on the work done by the system. Therefore, pressure and volume have to change, right? So what can we say for isothermal system then? Delta E will be 0, Q will be equal to W. Entire heat energy will be equal to the work done by the isothermal process, the thermodynamic system. Got this? Okay. Fine. Then we have, let's first go to isochoric process. Here, entire heat energy, just put a box around this, okay? Highlight this on your notes. The entire energy has been utilized by the system to perform the pressure volume work. Fine. Now isochoric process. Okay, what remains constant?
Pressure.
Isochoric. Bar is pressure. Isochoric
Volume.
Volume remains constant. Again, let's take a system. Fine. Let's take a system. This is a thermodynamic system under study. So this is P1, this is V1, and this is T1, right? So you are giving energy. Pressure becomes P2, volume becomes
V1.
Right. Temperature becomes
T2.
Correct. Only volume change. Now, is there, only pressure and temperature change. Is there any change in volume?
No.
No. So this will remain there. Right? This will remain there. Now tell me, has any work been done by the system?
Apparently
Pressure
not.
No. Of course no. There is no pressure volume work. So the work will be 0. But is there any change in temperature?
Yes.
Yes. So the entire energy that has been supplied to this system has been utilized by the system to change what? Temperature. What does that mean? Temperature and pressure. What does that mean?
Internal energy changes.
Internal energy has changed. So Q is equal to delta E plus W. So Q is equal to delta E plus 0. Q is equal to
delta E.
Right. So the entire energy supplied to an isochoric process while it goes from initial state to final state is utilized in changing the internal energy of the system. Okay? So in this process, the Q will be equal to delta E. Okay? Anything else? No. Fine. And work done here is 0. Okay? You have to remember this. Work done here is 0 and Q is equal to delta E. And here delta E is 0 because temperature is constant. Therefore, Q is equal to the work done. So you can say these are kind of opposite to each other. Okay? Isothermal and iso. That's why I took this first. Isochoric process. Now coming to adiabatic process. What did I say in an adiabatic process?
No exchange of energy.
No exchange of energy with the surroundings. So whatever change is brought, P1, here all the three change. P1, V1, T1, P2, V2, T2. Okay? No exchange of energy. Q is not supplied. Q is not supplied. Since we have not supplied any external source of energy, okay? But then something has happened with the system. How did this happen? Because for some work to happen, we need energy, right? So energy can neither be created nor destroyed. Then how did this happen? Okay? So whatever happened to this system happened at the expense of its own energy, internal energy. Whatever this system did at the expense of its own energy. That's at the expense of its internal energy, right? So you can here say, let's say this is work done, okay? This is work done. Let's say the internal energy of this was E1 and finally it became E2. Initially the internal energy was E1 and finally it became E2. So the work done by the system would be E1 minus E2, right? Initial internal energy minus final, the change in internal energy would be the work done, right? The amount of internal energy utilized was converted into work done, right? It was converted into the work. So we can say, but in thermodynamics, change in internal energy means increment in internal energy, which is actually what? E2 minus E1. I mean, whenever in thermodynamics you'll see delta E or whatever delta something, it means final minus initial. So you don't have to get confused. Okay, so W here would be minus of delta E. Okay, which also means that here this has been utilized, right, to perform the work done. So here, what would Q be? Q is equal to W plus delta E, right? And Q here is
energy.
Is there any supply of energy from external source? So it is 0. And W is
minus
W is delta E. Okay?
minus delta E.
W is equal to minus delta E. Here, delta E plus W. So W will be minus
delta.
Okay? So in an adiabatic process, pressure, volume and temperature of the system change, but the work happens at the expense of its internal energy. So work would be equal to minus delta E. Okay? Now coming to Isobari process. So you understood all these. Okay? Now coming to Isobari process. What remains constant?
Pressure.
Pressure remains constant, right? We'll again take a system, a thermodynamic system. Pressure is P1, volume V1, temperature T1, right? You give external source of energy. Pressure becomes
P2.
Pressure remains P1,
constant.
right? Pressure remains P1, volume becomes V2 and temperature becomes T2, right? Now here, has volume changed?
Yes.
Yes, so it has performed some work, right? Let it be this much. This is W. I hope I'm writing it clear. Am I?
Yes.
W, okay? So some work has been performed by the system. Now see, in going from initial state to final state, the pressure has remained constant and temperature has
changed.
What does that imply? When the temperature of the heat has absorbed heat and absorbed heat and absorbed heat, so that its temperature rose. What happened to the internal energy of the system?
Increased.
It increased, correct. So there's a change in internal energy. I already told you internal energy is a function of temperature. So when the temperature of the system has changed, that means internal energy of the system has changed, right? So we can say Q, the external source of energy in the form of, let's say, heat that we supplied, we know is equal to delta E plus W, right? And here Q, do we have delta E?
Yes.
Yes, we have delta E. And do we have W? Has work been performed? Yes, work has been performed. So here, the external energy that you supply will be utilized by the system to increase its internal energy, to change its internal energy, plus to perform some work, right? So in this case, Q is delta E plus W, okay? And pressure remains constant, okay? And work done is not zero. Work has been done here, okay? Got this? In isothermal process, the external energy that we supply is entirely used up. Now remember all these points, these basic bottom lines, okay? The external source of energy that you supply in the case of isothermal process, okay? The external source of energy is completely utilized to perform work by the system, okay? To perform work by the system. So, and therefore internal energy internal energy does not change, okay? You have to remember this, internal energy does not change, entire energy is utilized to perform work, right? In an isothermal process. when this happens, then only the temperature can remain constant. Okay. Then in an adiabatic process, you do not supply any energy. Okay, let's come to this first. When you give external energy, okay, the entire energy is because the temperature is changing and there is no change in pressure or volume. When there is no change in pressure or volume, no work has been done. So the entire external source of energy is utilized in changing the internal energy of the system. Okay, is utilized in changing the internal energy of the system. Here, isothermal, Q is W, whole Q utilized for W. In isochoric, whole Q utilized for changing E, right? Here, now in adiabatic process, you don't have any external source of energy. Whatever happens within the system, okay? So here, the work has been done because there is a change in volume. So piston has gone up, right? Work has been done. So whatever work has been done has happened at the expense of internal energy of this system because outside energy is not being given, right? So entire work has been done at the expense of its own energy, its internal energy. So work would be equal to the taking up of energy, change in internal energy minus delta E, right? Then isobaric process, pressure remains constant. The external energy has been utilized in both. Changing the internal energy, how do we know that? Because temperature has changed. And in the work performed by the system, how do we know that? Because volume of the system has changed, piston has gone up, right? So for an isobaric process, that process where pressure remains constant, the energy that you supply to the system is utilized for both changing the internal energy and performing work. Okay, clear? You have to remember these processes forever. Then coming to our next topic. Have you heard about reversible and irreversible processes?
Yes.
Yes, you have. For example, we say we cut a page, okay? Just cut it down into pieces and throw it. Can you reassemble it into a single page?
No.
So you call it a irreversible process, right?
Right.
This is a general process. So in general terms, what do you say? You say if you can just reverse something, it's a reversible process. If you cannot, it's an irreversible process, right? And in terms of chemical reactions, what do you say? For example, we have this reaction, very common reaction, okay? We synthesize ammonia. You say this is a reversible reaction, right? Because this reaction can go in this direction, but it can also go in the reverse direction. So you call it a reversible process. But in thermodynamics, you cannot say this. What did I tell you thermodynamics is all about?
Energy change.
Energy change, exactly, correct. Thermodynamics is all about energy changes. Energy changes accompanying your system under study, right? So when you talk about irreversible, reversible reactions in thermodynamics, you have to take into consideration the energy changes. That means for a thermodynamic reaction, for thermodynamically to be reversible or irreversible, the energy changes should also be reversible. Should in fact be reversible, right? Then only you can say that a thermodynamic process is reversible. But tell me from common sense, is it possible for energy change to be reversed with the surroundings? I mean, I already told you surroundings means the whole universe. Whenever some energy in the form of, let's say, it goes into the surroundings, some energy, it goes into the surroundings. Can you go to the surroundings and get that energy back?
No.
Practically, it's not possible. So thermodynamically, ideally, no process is thermodynamically reversible. Okay, no process is ideally thermodynamically reversible. But for the sake of study, we do say thermodynamically reversible and irreversible. How is that possible? I will tell you. Okay, let's take this reaction again. For any process to occur, there is a driving force and there is an opposing force. Okay, there are two forces. For this reaction, let's say N2 plus H2 gives NH3. Okay. For this is not a thermodynamic process. I mean, this is a thermodynamic process, but this is not the system that we will study to understand reversible and irreversible. This is just an example. N2 plus H2 gives NH3. Now here, this is the driving force. for ammonia, to form ammonia, this is the driving force. What is the driving force? That force which will combine nitrogen and whatever reaction happens, whatever is the mechanism of reaction, the driving force is that force which will combine nitrogen and hydrogen to form ammonia. Okay, and this is the opposing force, that force which will again break it down into nitrogen and ammonia and will not let ammonia to form. Okay, that is the opposing force. For a reaction, so, okay, now if the driving force completely overcomes opposing force, what? Driving force
completely overcomes
the opposing force. That means this force does not come into play. Only the driving force comes into play. What does that mean? This reaction will not go in this direction, and then this process will be, the reverse direction will not happen. The process will be
completed
irreversible, because this direction, the process will not occur in this direction. The driving force has completely overtaken the opposing force, so it will only drive it towards this side. Okay, so the reaction will be
irreversible.
The process will be irreversible. That means for a process to be irreversible, the driving force completely has to overcome the opposing force. Then only it will be irreversible. What about the opposing force completely overcoming the driving force? It doesn't make any sense. Yeah, it doesn't make any sense, because if you say this force completely overcomes this, then this becomes the driving force and this becomes the reaction. Yeah, this becomes the irreversible reaction. Okay, so this is one and the same thing. Now, if driving, did you understand what I said? Yeah, students will. The driving force is equal to the opposing force. Driving force and opposing force are equal. What will happen?
It won't happen.
It will happen, but an equilibrium will be maintained. That's what you call as thermodynamic. Equilibrium has come into play. That's why we show this sign, because this force and this force are equal. So an equilibrium will occur, which is actually called as a reversible process. Okay? This is what you call as a thermodynamically reversible process, where the driving force and opposing force are
equal.
Yes. This is called a reversible process. Now come to a thermodynamic system, our thermodynamic system. Okay, let's erase this also, this will create confusion. This is our thermodynamic system, right? This is our thermodynamic system. Now this is the system, the whole universe is the surrounding. Now for this system, whatever change happens in this system, this piston goes up, this piston goes down, whatever change we bring about, while going up, the volume changes, the pressure changes, okay? Whatever change we bring in this system, it will be said to be reversible only if the energy change that happened between this system and the surrounding will remain constant. That means there will be ideally no energy change, okay? So let's suppose the change that we want to bring about is increasing the volume, okay? We have to increase the volume. To increase the volume, this piston has to go up, right? So this is the driving force and this is the opposing force, okay? Now for this piston to go up, here this decrease in pressure here is the driving force that will send this piston up, right? This increase in pressure is the opposing force. This decrease in pressure is the
driving.
You got my point? How? When this gas will relax, the pressure will decrease. That means, and when this gas will relax, the volume will increase. The piston will go up. You got it? So the decrease in pressure here is the driving force, and increase in pressure on this piston, the external pressure. I already talked about external pressure and internal pressure. The external pressure will be the opposing force. Okay? So here, let's say we have very small particles on this piston. Very small particles on this piston. What we do is we pick up one small particle, very, very infinitely small particle. The pressure will change how much?
Very small change.
Very small, dP, right? The pressure will change dP. So what's the total change of pressure? P minus
dP.
dP. There's a small change in pressure here and the piston will go
Slightly up.
slightly up. Infinitesimally slowly, you call this. Infinitesimally slowly. You pick just one particle and this piston goes just slowly up. So the energy change that occurred between this system and surrounding for this infinitesimally slow change is very small, almost negligible. Almost negligible. Now, to move it further, you will pick one more particle. So it will again go very slowly and the energy change will be almost negligible. This is the way you bring about a reversible change in a thermodynamic system. You perform the work such infinitesimally slowly that the energy change between the surrounding and the system almost remains negligible. Rather than you just let this piston go suddenly up, the energy change would be huge, right? Then the process would be irreversible. So for a thermodynamic process to be reversible, you have to bring about the change infinitesimally slowly, okay? So that the energy change that occur between the system and the surroundings would be negligible, okay? Got it? This is what you call as thermodynamically reversible. Now you have to forget, in thermodynamics you have to forget that reversible and irreversible process. You have, for thermodynamic process to be reversible or reversible, you have to keep into consideration the energy. Otherwise it was a reversible process. Take the piston up, get it down. Take it up and get it down. But for thermodynamic process to be reversible, the energy considerations have to be taken into point, right? So I hope you understood what is a thermodynamically reversible and irreversible process. Should we continue or this is enough? Enough, okay? So this is all for today. In our next topic, we will now this up to here we were learning about the thermodynamic language only, okay? Now we will take up real thermodynamics, the terms of physical quantities of thermodynamics, enthalpy, entropy, all those things. We will learn one by one what are they and what are their relations and what is the significance of their relations, okay? Maybe the classes are resumed by then, I don't know. I wish you all a happy learning. Take care.